Alkenes can be prepared from alkynes, alkyl halides, vicinal dihalides, and alcohols. Let's look at each of them in detail. To obtain alkenes from alkynes, we carry out partial catalytic hydrogenation. During this reaction, addition of a hydrogen molecule, that is, addition of two hydrogen atoms, takes place across the triple bond of the alkyne. There are two catalysts that are commonly used. One is palladized charcoal, which is partially deactivated using compounds like barium sulfate or quinoline. It is also known as Lindlar's catalyst. The other catalyst is sodium in liquid ammonia. For example, ethine, on reduction with palladized charcoal or sodium in liquid ammonia, forms ethane. Similarly, propine, on reduction with palladized charcoal or sodium in liquid ammonia, forms propene. Depending upon the nature of the catalyst used, a higher alkyne can be reduced to cis or trans alkene. Lower alkynes, such as ethine and propine, and higher terminal alkynes do not yield cis-trans isomers upon hydrogenation. When the catalyst used is Lindlar's catalyst, the alkene obtained shows cis geometry. When the catalyst used is sodium in liquid ammonia, the alkene obtained shows trans geometry. For example, 2-butene, on reduction with palladized charcoal in presence of quinoline, forms cis-2-butene. However, 2-butene, on reduction with sodium in the presence of liquid ammonia, forms trans-2-butene. Alkenes can also be obtained from dehydrohalogenation of alkyl halides. When an alkyl halide is heated in presence of alcoholic potash, it gives an alkene and one molecule of halogen acid is eliminated in the reaction. The hydrogen atom for the halogen acid is obtained from the carbon atom adjacent to the carbon atom attached to the halogen atom. The carbon atom attached directly to halogen is called alpha carbon, whereas the adjacent carbon is called beta carbon. Hence, the reaction is known as beta elimination reaction. As hydrogen and halogen atoms are removed in the form of halogen acid from alkyl halide, the reaction is also known as dehydrohalogenation reaction. For example, 1-chloroethane, on heating with alcoholic potassium hydroxide, forms ethene. During this reaction, the hydrogen and halogen atoms on adjacent carbon atoms of 1-chloroethane are eliminated in the form of hydrochloric acid. In a dehydrohalogenation reaction, if there are two possible positions where the double bond can be formed, then the product obtained is governed by Saint-Zeff's rule. Saint-Zeff's rule states that elimination would predominantly proceed to the formation of olefin in which the double bond is highly substituted. In other words, the hydrogen atom will be removed from the carbon atom possessing lesser number of hydrogens. The rate of reaction depends on the nature of alkyl group and the halogen respectively. The rate increases from primary to tertiary alkyl halides as shown here. The rate is also affected by the halogen atom attached and is the highest for iodine and lowest for chlorine. Another way to obtain alkenes is by the dehalogenation of vicinal dihalides. In vicinal dihalides, the two halogen atoms are attached to two adjacent carbon atoms. When such dihalides are treated with zinc metal, the zinc atom removes the two halogen atoms, forming zinc halide, leaving behind an alkene in the process. This reaction is also called dehalogenation, as zinc removes two halogen atoms simultaneously. For example, when dibromoethane is treated with zinc, it forms ethene and zinc bromide. And when 1,2-dibromopropane is treated with zinc, it forms propene and zinc bromide. Alkenes can also be obtained from alcohol using acidic dehydration process. When heated with concentrated sulfuric acid, the OH group of the alcohol and one hydrogen atom from the adjacent carbon atom are eliminated in the form of a water molecule, forming an alkene. Hence, the reaction is said to be acidic dehydration of alcohol. An example of this would be the dehydration reaction of ethanol on heating with concentrated sulfuric acid to form ethene. During this reaction, the hydrogen atom and the hydroxyl group from adjacent carbon atom are eliminated in the form of water to form ethene. Dehydration takes place in three stages. First, the alcohol is protonated by the acid catalyst to form a protonated alcohol. Secondly, the protonated alcohol loses a water molecule to give a carbocation. Finally, the carbocation formed loses a hydrogen ion and forms a double bond. Satzev's rule also governs the dehydration of alcohols. For example, in the dehydration of 2-butanol, there are two possible positions for the double bond. However, 2-butene is more substituted than 1-butene. Hence, the more predominant product is 2-butene. Thus, we see that alkenes can be obtained by many different methods. Now let us look at the physical properties of alkenes. Alkenes are colorless hydrocarbons. Except for ethene, all the other alkenes are odorless as well. The first three members of alkene homologous series are gases. The 4th to 14th are liquids, and all members above 15th are solids. Being non-polar compounds, alkenes are insoluble in water, but soluble in non-polar solvents like benzene and petroleum ether.